This is our video
for the Engineering Grand Challenge
of developing carbon
sequestration methods. There are many ways to go about this. Some are better than others, and we definitely haven't discovered everything there's need to know about carbon sequestration. Next, we're going to talk about why it's important to develop these methods.
Why is carbon sequestration a grand challenge? Increasing CO2 emissions could impact the environment. It also can lead to ocean acidification, which means a lower in pH, more acidic, which could impact coral reef. It also leads to a rise in global temperatures. And yes, it could lead to presidential debates. It leads to ice melting of glaciers. And last but not least, we could end up being on Planet B.
Carbon dioxide is known as a greenhouse gas. CO2, along with the other greenhouse gases, get their name from the heat-trapping qualities they have similar to those of the roof of a greenhouse. Short light waves from the sun that enter through the atmosphere are able to pass through these greenhouse gases, but when these waves reach Earth, they heat it, which the Earth then releases. Greenhouse gases trap these longer heat waves and send some back to the Earth, therefore making the Earth warmer. To an extent, greenhouse gases are necessary to keep the Earth warm and make life possible, but in excess they can heat up the Earth too much, causing global warming.
How the heat trapping leads to global warming. The heat that's trapped in our atmosphere acts as a blanket and it holds in the heat, which warms our planet. The greenhouse gases act as a greenhouse. The glass walls of the greenhouse let in the heat but also trap the heat, so it stays warm all the time. The carbon dioxide traps in heat and doesn't let any heat out, so over time our global temperature rises and the Earth becomes warmer. The global temperature has risen more than 1 degree Celsius since 1880, which doesn't seem like much, but it only took a 2-degree drop to put the Earth into a little ice age. The number of air molecules with CO2. In 2019, the global average of carbon dioxide in the atmosphere was about 409.8 parts per million, which is the highest they've been in 800,000 years. CO2 makes up about 0.04% of the atmosphere, which doesn't seem like a lot, but it used to make up 0.018%. There has been an 11% increase since 2000. These small changes in percent cause big effects.
Other than global temperatures rising, carbon dioxide can still cause harm to the planet by stuff such as ocean acidification. Because of the amount of the carbon dioxide in the atmosphere, the ocean is now absorbing it, changing the pH levels. The ocean's current pH is around 8.1, but it's slowly becoming more acidic. As the ocean becomes more acidic, this harms shellfish and other marine life that we depend on, which in turn can harm us. Now, all of that brings up the question, how do we go about capturing the carbon from the atmosphere? One of the ways we can catch carbon is to catch it after burning fuel in a post-combustion method. This method can be applied to conventional power plants. Carbon dioxide is captured from exhaust gases at power stations, and absorption towers would have to replace the smokestacks where the CO2 would be taken out of the emissions by chemicals. Then a second tower would collect the CO2 from the chemicals so that they could be used again.
Burning coal in pure oxygen and not air. Instead of burning coal in air, burning it in pure oxygen makes it much easier to separate the carbon dioxide because it would only be mixed with water vapor. This is important because once it's separated, it can be piped away to store instead of releasing it into the atmosphere. But this isn't easy to do because creating pure oxygen is not cheap, but if it was made economical, it would be a great way to reduce CO2 from going into our atmosphere.
To continue our presentation of carbon sequestration, the question that I would like to pose is, can carbon sequestration reduce global warming? An intergovernmental panel on climate change concluded that sequestration and reduction of emission over the next 3 decades will have a substantial impact to stabilize levels of CO2. So here's a short explanation to mitigate the increased temperature caused by CO2. So some aerosols have the ability to scatter sunlight. This includes pure sulfates that reflect the sun's radiation and thus cool the atmosphere. This is known as stratospheric aerosol injection. So this technique is based upon a natural event. The eruption of Mount Pinatubo ejected 20 million tons of sulfur dioxide, thus creating sulfate aerosol, and this reduced the global temperature by 0.5 degrees. Here is a graphical depiction of the same. Here are some visuals of a volcanic eruption. Yes, it is hard to believe that this eruption resulted in the decrease of global temperature. The engineering technique involves a plane spraying tiny sulfate particles at around 60,000 feet and thus cooling the planet. But this also comes with a set of challenges, such as altitude and expense.
Now that we've figured out how to capture the carbon, we need to figure out how to store it. One of the ways people have thought about storing it is using underground methods. Engineers found a way to store CO2 underground by using old and depleted oil and gas fields. This can be convenient because the carbon dioxide interacts with the oil that's already there, making it easier to remove. This is also an advantage because carbon dioxide reduces the friction of the oil flowing through the rock to the wells.
However, there are some faults to this method. One of these is that the underground CO2 could possibly leak out into the atmosphere over time. The storage security calculator was developed to see what would happen if billions of tons of CO2 were injected into the ground over 10,000 years. This option for storage could be available by 2050, and if locations are chosen right, then leakage could be reduced. Another option for sequestering excess carbon is the use of sedimentary rocks. Sedimentary rocks have large pore volume and connectivity that could seal the carbon in well. The injected carbon in these sedimentary rocks dissolves into saline groundwater. Another process involving rocks is carbon mineralization. Typically this occurs with igneous and metamorphic rocks. When carbon is around certain rocks, it can become a solid mineral such as carbonate. This could be a great option because the carbon, once solid, is not able to escape into the atmosphere. One version of this is when the carbon is injected underground to form minerals. The second option is to expose the carbon dioxide to ultramafic rocks or basalt at the surface as opposed to underground.